Hi all, and thank you for watching this talk. So I'm going to talk about improved monotonicity testers via Hypercube embeddings. This is joint work with Mark Braverman, Subhash, Khot, and Kindler. So let's get going. So we're going to start with describing the monotonicity testing problem, and we're going to start with the most classical domain it has been studied on, which is the uniform hypercube. So what is the hypercube? Well, you look at the set of vectors 0, 1 to the n. This is going to be your domain, and you equip it with a partial order. So in that partial order, x is less or equal to y, if and only if xi is less or equal to yi for all coordinates I. And once you have a partial order, you can define monotonicity testing in an actual way. So a function on the hypercube is called monotone if whenever x is less or equal to y, it holds that f of x is less or equal to f of y. In other words, f has to respect the partial order on 0, 1 to the n. And once you have the partial order and monotonicity, you can define the monotonicity testing problem. So in this problem, you are given an oracle access to a function f, to a Boolean function on the hypercube. And this function is promised either to be monotone, or else it's promised to be far from monotone. And the measure of distance here is the normalized Heming distance, meaning the distance between f and monotone is you take the minimum over all functions g, which are monotone, you count the number of inputs x on which f and g differ on, and you divide it by the total number of points on the hypercube, which is 2 to the n. So if this fraction is at least epsilon, then we say that f is at least epsilon far from monotone. And for this talk, you should think of epsilon as a small constant. You can do anything with dependency on epsilon, but it's a bit annoying, so we don't want to do it. And the question is, how many oracle access queries do you need to make to f in order to distinguish between these two cases? That is, you want to design an algorithm that makes as few query access as possible to f, and accepts with probability 1 if f is monotone, whereas it rejects with probability close to 1 if f is epsilon far from monotone. So monotonicity testing has been around for a while, in fact for over 20 years. It was first introduced in a paper by Goel et al., who also gave an OFN query tester for the problem. And this tester is a very natural and very nice one. It's called the edge tester. And in that, you just pick 2 points x and y that differ on exactly one coordinate, chosen randomly. You query the value of f on these 2 points, and you reject if these 2 values violate monotonicity. So it's a very natural tester, and the analysis of Goel is very, very nice. But this is the best you can do if you only consider edge testers. And it took a while to improve upon this tester, in fact, over 10 years, until Chakrabarty and Sadri showed different tester, which achieves query complexity n to the 7 over 8. So the tester is different. The tester is what is called path tester. So again, it's some base tester that only does 2 queries, which is then repeated numerous times. And the base tester just takes 2 points x and y that in this case, they are not different on only one coordinate, but rather they are different on several coordinates between one root and many. So they already had to come up with a new test, but the real interesting thing in this work is the analysis of the tester. So the analysis of the tester relies on a very interesting directed version of an isopragmatic inequality due to Margulis, which they had to prove, and then used in order to analyze this path tester that I just mentioned. And following their work, the analysis of the tester was improved by Chen et al. To n to the 5 over 6. So really the tester and the analysis at heart are the same. They still use Margulis as a monotonicity inequality. And in fact, this is the best you can do as long as you're only using Margulis type directed versions of isometric inequalities. And a few years after that, together with Khot and Safra, we managed to improve upon this result and got a root n tester. So this tester was again a path tester, very similar to the one by Chakrabarty and Seshadri. And the real difference here between this work and previous works is that we use a different isoperimetric inequality. In particular, in that work, we proved a directed version of an isoperimetric inequality due to Talleyrand, which is stronger than the variant by Margulis, and we used it to design a tester and analyze it. And because root n is the best you can do, at least as far as non-adaptive testers are concerned, due to work by Fisher et al., this finishes the discussion about monotonicity testing over the Hypercube, because the complexity is exactly theta of n, maybe up to Poilov's. So what I'm going to talk about today is how about monotonicity testing over other domains. So what do we mean by other domains? Well, you can consider any partially ordered set and study the monotonicity testing problem over it. But I would like to argue that to get interesting results, you need a little bit more structure, because partially ordered set can be very wild, and it's not clear what you can even say about them. So in this work, we consider what is called product domains, which is you have some basic domain, some basic probability space, m, comma mu. So you should think of m as constant. The case of the Hypercube is just m equals 2. But you should think of m as like 10 or 20 or something like that. And mu is some probability distribution over m. And you should think of m as being equipped with the ordering which is natural, 0 less than 1, less than 2, less than so on and so forth. And once you have this, you can tensorize this space in order to get m to the n equipped with the product measure mu to the n. And then you can discuss monotonicity testing over this product domain. So you have the partial ordering induced by the basic partial ordering. You have the notion of monotonicity, and the only thing that you need to define is the notion of distance from monotonicity, and this is defined on the slide. So the distance between f and monotone with respect to a measure mu is the minimum over all the monotone function g of the measure of the set of points x on which f and g differ on. So usually you should think of mu as uniform, but it's not always going to be the case. And I'm going to mention when it is not going to be the case. So once you look at this problem, and especially if you are familiar somewhat with the testers for the Hypercube, some testers immediately spring to mind when you look at this domain, which is called the hypergrid. So there are clear analogs of the edge tester of Goldorf et al., as well of the path testers. But the slightly annoying thing is that it's not clear how to analyze them. So while it is clear that these are supposed to be the right testers, the analysis that we had for the Hypercube does not generalize, or at least we don't know how to generalize it very easily, to the hypergrid. So there is an exception of the approach of Goldorf et al., which is kind of easy to generalize to the hypergrid, and therefore we did know of an correct complexity tester that followed the approach of Goldorf et al., but up until 2018, this is the best that was known. So that was the case until a few years ago, where Black, Chakrabarty, and Seshadri showed that you can improve upon the Goldorf et al. Result again. And indeed, there is an n to the 5/6 correct complexity testers for testing monotonicity over the uniform hypergrid. And interestingly, what they managed to do in this work is they did manage to generalize some of the directed isoperimetric inequalities from the cube to the hypergrid. And more specifically, they managed to generalize the Margulis-type isoperimetric inequality due to Chakrabarty and Chaudhry, and then converted it into a tester in the same way. So the real novelty here is that they managed to prove the isoperimetric inequality over the hypergrid, and this is really non-trivial. So it's not like the same proof, but you need to do some other things. And probably what you expect me to say now is that in this work we managed to improve this result to square root of n. And to do that, we just generalize the Talleyrand style isoperimetric inequalities. But I would like to say that, but the issue is that I don't know how to generalize the proof. And sort of the issue is that the proof that we had for the Boolean cube was very specific to the Boolean cube. So in that proof, we had to define some operators that have no clear analogs for the hypergrid, and therefore the proof seems to be very tailored to the cube. So I'm not going to say that, but nevertheless, I'm going to tell you that in this work, we do manage to get off square root of n for complexity testers for the uniform hypergrid. And in fact, you can do any product measure as you like. And as a byproduct, we also get directed version of isoperimetric inequalities in the style of Talleyrand. And what is very different from the previous approaches is that the proof. So we're not trying to generalize some facts about the Boolean hypercube, and instead we take a different route. What we do in this work is we manage to do a reduction between testing monotonicity over the hypergrid to testing monotonicity over the hypercube. Namely, the main goal in our work is we're given a function f over the hypergrid, and we wish to construct a function g over a slightly larger hypercube of dimension n prime. And we want the following properties. We want that a query access for g can be simulated by query access to f. Secondly, we want this transformation to preserve distance from monotonicity. In particular, if f is monotone, we want g to be monotone. And if f is far from monotone, then we want g to be also far from monotone. And lastly, we want the dimension n prime of the g function to be not too much larger than the dimension of f. And in particular, we would like to be n maybe times some polylogs of n. And if indeed you manage to find such construction of g that satisfies all of these properties, you can simulate the monotonicity tester for g using query access for f, and you can show that this would test monotonicity for f, and the query complexity would be root of n prime, which is the same order of the root of n because we want the dimension to be roughly the same. So this is the approach that we try to take in this work. And of course, now the question is, how do you do this reduction? So in the rest of the talk, I'm going to illustrate how you do it for the case of the p-bias cube, which is, again, something on the hypercube, but with a different measure. And then I'm going to say a few words on how you do it for the hypergrid. So to illustrate the idea, we're going to take a very concrete cube. We're going to consider the quarter bias cube. So here again, we have 0, 1, but now we have a different measure on it. We have the measure mu quarter, which assigns 1 probability quarter and 0 probability 3 quarters. And what we want to do is we want to reduce testing monotonicity over such measures to that over uniform bits. And when you look at this, especially the number quarter, the natural idea that comes to mind is the following. So if I take two uniform bits, x1 and x2, and I take a product of them, then I would get a bit which is has bias quarter. So let's try to use this fact in order to define our function g. So indeed, we're going to define a function g which has a dimension which is double that of f. And when it gets as input x1 to x2n, it's going to compute the pairwise products, x1, x2, x3, x4, and so on and so forth, get an n vector string, and plug in it to f. So this is going to be our construction of G that attempts to simulate a quarter by uniform bits. And indeed, you can show that if you want to answer queries to G, you can simulate it via queries to F. This is clear just by definition. No? And secondly, it's also clear that if F is monotone, then G is monotone also. And what seems like it should be the case, but it's not completely clear, is what happens if F is far from monotone. In that case, we would like to say that G is far from monotone. And, this makes a lot of sense, right? All of the simulation here seems to be the correct way. And it seems true, but how do you show it? And the issue here is that we don't have many tools to show that something is far from monotone. So let's try to do it nevertheless. So we have this function G that we defined on the previous slide. And we want to show that if F is far from monotone, then G is far from monotone. Well, equivalently, it means that we want to show that if G is close to monotone, then F is close to monotone. So far we didn't do anything. This is logically equivalent. But now we have an assumption. We have an assumption that G is close to monotone, meaning there is some function H, which is monotone on dimension 2n, which is close to G. And our goal in life is to show that F is close to monotone, and it only makes sense that we're going to do it by constructing explicitly a function h prime on dimension n, which is monotone and close to F. And really all that we have in order to construct h prime is this little h above. So how are we going to use it? Well, we want to define h prime of y, where y is some input from 0, 1 to the n, and we only have h in our hand. So the only real thing that we can do is generate from y some input x of dimension 2n to h, and then define h prime of y to be h of x. So, to go from f to g, we apply this map that sends x1 to x2 to the product of x1, x2. And now, in some sense, we want to go the other way. So it makes sense that if you have this y and you want to generate x, you should use the pullback according to this map. So what do I mean? Well, if y1 is equal to 1, then you really have no choice. You must take x1 and x2, the coordinates corresponding to y1, to be 1, 1. But what if y1 is equal to 0? So in that case, there are three options, 1, 0, 0, 1, and 0, 0. And it's not clear which one of them to pick. So pick one of them uniformly at random. To be more precise, what you're going to do is, for each coordinate I, you're going to pick vi, which is either 0, 0, 1, 0, 0, 1, independently of the rest of the coordinates. And this is going to be the pullback of 0 on that coordinate. And once you have made this choice for each coordinate, you can define the pullback map corresponding to these choices, which pulls 1 back to 1, 1, and pulls 0 back to vi. And once you have that, you have this association from y to x. You can define the function h prime as above. And if you carry out a simple calculation, you can show that in expectation over the choice of the pullback, the distance between h prime and f is the same as the distance between h and g, which is most delta. And you can also observe that h prime is always monotone. So therefore, it means that f is delta close to monotone, and we're done. So this indeed shows that you can reduce quarter-biased to unbiased cube. And in a similar way, you can actually do any p-biased cube for p which is power of 2. And once you have that and you use some other elementary manipulations, you can actually get any p-bias that you'd like, and the query complexity is still of n. But this idea, as I presented it, seems very specific to the Boolean cube again, and it's not clear what to do about larger alphabets. So to see what to do about larger alphabets, you have to sort of take a step back and see what was really happening in this argument and what made it work. And really the point of this argument is that we had one way to go from 0, 1 squared to mu quarter by taking the product operation. And then we also had this pullback operation that goes from y to one of the x1, x2 that made that product into y. And this maps had to satisfy mysteriously several properties, so they had to preserve measures and all of that. But additionally, they had to be monotone. This is really the property that we used in the proof. So for the product map, it is clear that if you take x1, x2 and map it to x1, x2, this is monotone. And for the pullback, it's also clear, but it's a bit hidden under the surface. So for every choice of VI that you made, the pullback operation that you get is also monotone. So with this in mind, can you construct embeddings for the hypergrid? Maybe through the down. And once you think about it this way, there is a very natural attempt that you may do, which is called a threshold embedding. So here you're going to attempt to partition 0, 1 to the r into 3 parts according to the Hamming weight and try to make it as equal as possible. And indeed, if you think about it for a little bit and use some estimates, you can show that indeed you can partition the cube into 3 roughly equal parts, and you use these thresholds as on the slide. And this is monotone, and you have a pullback, and all of this is very good. The only issue is that it's not actually possible to make this threshold function partition the cube into 3 equal parts. And in fact, it will always be the case that one of the parts will be at least somewhat off. So trivially, you can achieve 1 over root r, and if you work a little bit harder, you may improve that a little bit, but this cannot give us like exponential in our distance from uniform. And when you think about that, this means that the r that you're going to take here is going to be large, which is going to lead to a blow up in the dimension, which we don't want because it affects our query complexity. So nevertheless, and this is where most of the heavy lifting in the paper is, we show that you can take this, roughly this construction, and slightly shuffle it and do stuff to it in order to balance it out so that it partitions the cube into 3 roughly equal parts in a way that preserves monotonicity as well as the pullback of the properties that we need. And to prove that, we use a notion which is called monotone matchings, which is matchings that are only taking monotone edges or monotone pairs on the hypercube, and this is where most of the work goes in. And formally speaking, what we really have to prove is that you can partition the hypercube into 3 roughly equal parts, as equal as they can be, because 3 is an odd number, so that between any 2 parts there is a perfect monotone matching. And in fact, you can do it for any number of parts, any constant number of parts. There is nothing special about 3. And this is how we construct embeddings for the hypergrid. So this is how we prove our results. And in a concurrent work, Black, Chakabani, Sadri managed to prove the same result about the hypergrid on the uniform measure. So the tester is really the same, but their analysis is completely different. So they follow the same framework as in the hypercube, except that in their work they managed to directly generalize the Talagrant style isochromatic inequalities for the cube, and then use it to construct the tester. But this takes some serious effort, and indeed they do some non-trivial work. So this seems like it finishes off, these two works finish off the monotonicity testing problem over the hypergrid. Except that, well, if you really want to completely finish it, there is one more case that you have to consider, which is what is the dependency on the alphabet size. So both our work and this work of Black, Chakrabarty, and Chaudhry get polynomial dependency on the alphabet size m. And there are some other works that say that you only need to consider m, which is polynomial size. In fact, you can do a dimension reduction. So it would be interesting to know if the polynomial dependency on m is necessary, or maybe it can be improved. And for all we know, you can do with logarithmic dependency on n, but these two works fail to get it. And another interesting question is whether there are some other domains in which it would be interesting to study monotonicity testing. So to make it interesting, it would have to be something which is non-product domain, but some interesting measure with enough structure. Maybe something from statistical physics, maybe the Ising model, who knows? So that's all. Thanks.